the micrometer. The most important measuring tool in machine shop work is the Micrometer Caliper, used to measure variations in size too small for the human eye to see. Different types of micrometers are used to measure inside widths or diameters, outside lengths or thicknesses, and the depth of holes or cuts, but the principle used by each is the same. The Micrometer Caliper, used in measuring thickness or outside length, has a sturdy frame on which is mounted a hardened steel anvil. This frame supports the barrel, which has a scale graduated in 25 1/1000ths of an inch. Inside this barrel is an internal screw. Engaging the barrel screw is one end of a hardened steel spindle. The thimble is part of the spindle assembly and contains a scale graduated to represent 1/1000th of an inch for each division. The micrometer uses the principle of the screw to control the movement of the spindle. The screw has 40 threads to the inch. 40 turns of the spindle move it 1 inch. Therefore, one complete turn of the spindle moves it exactly 1/40th of an inch. 1/40th of an inch is 0.025, 25 thousandths. The barrel is marked off in divisions, each of which represents a 25 thousandths movement of the spindle. Remember, one turn of the spindle moves it 25 thousandths of an inch. If we take the full distance around the thread and make a straight line of it, and divide that line into 25 equal parts or divisions, we will have a simple illustration of the scale which encircles the thimble. It is apparent that each division represents 1/25th of the travel of the screw as it makes one complete turn. Since one complete turn makes the spindle travel 25 thousandths of an inch, it is evident that each division represents 1/25th of 25 thousandths, or 1/1000th of an inch. Each division on the thimble represents a spindle travel of 1/1000th. The scale on the barrel is graduated in 25 thousandths of an inch. Each turn of the thimble moves the spindle the distance of one graduation. Each fourth graduation is numbered. 4 times 25 thousandths equals 100 thousandths. These zeros are dropped in order to make the scale easier to read. The complete scale on this micrometer shows that it has a range of 10 times 100 thousandths, or 1,000 thousandths, or 1 inch. Micrometers come in standard sizes designated by the largest opening of the micrometer and in steps of 1 inch. Most sizes, however, measure only 1 inch in thousandths. The 1-inch micrometer measures from 0 to 1 inch in thousandths, the 2-inch from 1 to 2 in thousandths, and the 3-inch from 2 to 3 in thousandths, and so on. The most commonly used micrometer is the 1-inch. Here the thimble is being turned to bring the spindle into contact with the work. The measurement is read by first reading the number fully visible on the barrel. This is 6. Remember that each of these figures should be read in hundreds. Therefore, it is 600 1/1000ths. Beyond the 6 mark, there is visible another graduation. This gives us 25 thousandths. On the thimble scale is shown the graduation that has stopped on the index line, the 1/1000th graduation. The full reading is 0.626, 626 thousandths. The ability to take accurate measurements with a micrometer depends on skill in its use. There is a feel to a micrometer that tells the skilled workman when he is using the right pressure in turning the thimble. Precise measurement can result only through proper use of the micrometer, and constant practice is the only way to acquire the necessary skill, to acquire the right feel. Until the operator is skilled in the use of the micrometer, he may measure the same piece at the same point and get different readings. Constant practice will develop the skill necessary to obtain uniform readings. Gentle pressure of the thumb and index finger on the thimble is sufficient to bring the spindle into contact with the work. As the spindle reaches the work, the drag of the fingers over the knurled surface of the thimble tells the operator when he uses the right pressure. The micrometer is a sensitive instrument for precision measurement and must be used with care. The good operator does not use it like a C-clamp, or swing it around when changing the setting, or lay it where it can drop to the floor, or where it can pick up abrasive particles or dirt. These things affect the accuracy of the instrument. Before using the micrometer, the careful operator removes all burrs and nicks from the work. The good operator makes sure that anvil and spindle are free of dirt or chips. The diameter of the shaft which has been measured is determined by referring first to the scale on the barrel. The figure 7 indicates 0.700. Two more graduations are seen. That's another 0.050, which is 50 thousandths. On the thimble scale, the number 1 graduation registers opposite the barrel index. That's 0.001. The diameter of the shaft is 0.751. Several places are gauged with a micrometer to check the diameter through the entire length of the shaft. The standard micrometer in experienced hands will give accurate measurements to 1/2 of 1/1000th or finer. Micrometers are often used in measuring 2 or more thicknesses of material. Since the combined thickness here is more than 1 inch, a 2-inch micrometer is employed. The figure that appears on the barrel scale is 7 or 700 thousandths. Then 2 full graduations of 0.025 each, that's 50 thousandths. The 0 on the thimble scale is exactly on the index line on the barrel. Remember, a 2-inch micrometer is being used, so 1 inch must be added. The total is 1.750. All micrometer calipers should be checked frequently, making sure that the 0 line on the thimble lines up with the barrel index. Those larger than 1 inch should be checked with special standards or gauge blocks. A 2-inch micrometer is checked with a 1-inch standard. When the micrometer is closed down over the standard with just the right tension and feel, it should register 0. A 3-inch micrometer is checked with a 2-inch standard. Larger instruments are checked with correspondingly larger standards. A companion tool to the outside micrometer is the inside micrometer. On the inside micrometer, the jaws or points expand to fit the part to be measured. The micrometer is held square with the inside surfaces of the work, and the measurement taken across the center of the hole. Another type of inside micrometer uses rods to measure the diameter of large holes. Rods of various lengths are inserted in the instrument according to the size of the hole to be measured. Accurate measurements of very large bores can be taken with this convenient tool. Other convenient tools for measuring internal diameters in medium-sized holes are telescoping gauges, which are shaped like the letter T. One arm is movable. A screw locks it in place. It's often used for checking the diameter of cylinder bores and other deep holes. The setting of the telescoping gauge is measured by an outside micrometer. Another type of micrometer is used for the accurate measurement of the depth of holes, slots, and other depressions below surface locations. The depth micrometer has a slender rod that reaches easily into small holes and slots. Rods of various lengths adapt the instrument to measuring holes of various depths. Micrometers and micrometer measuring tools are used in every machine shop. If the micrometer principle is understood, these instruments are easy to read. If the right type of micrometer is selected, accurate measurements can be taken for outside measurements, and for inside measurements, and for depth measurements as well. If they are kept clean and used properly, on work clean and free from burrs, they will give the precise measurements that make modern mass production possible. All micrometers are precision tools, and the good operator takes pride in his ability to use them properly. He knows that the thimble should not turn too freely or too tightly, and that the anvil and spindle must be kept separated to prevent corrosion, and that they must be kept in adjustment to assure accurate readings. The good operator gives them this care, oiling them to prevent rust and corrosion, and keeping them in a protected place. Fixed gauges. An outstanding American contribution to the vast industrial growth of the present century is the development of mass production, which depends upon the interchangeability of parts, and this in turn depends upon accurate measurement and fixed standards of precision. Many special types of measuring tools have been devised for easy and rapid measurement to precise standards of the numerous parts, large and small, made by mass production methods. For example, this inspector is gauging mass-produced parts that will go into airplane engines using special gauges made specifically to the limits allowed for each part. Most of the measuring tools used in mass production are fixed gauges. Fixed gauges differ from other measuring instruments, such as the Micrometer Caliper, in that a fixed gauge is not adjustable while in use. Some fixed gauges, such as this snap gauge, can be adjusted within a narrow range of settings, but the settings made remain fixed. Every drawing contains the required information about dimensions, and where parts are to fit closely, you will find the allowable tolerances stated. For example, the diameter of this shaft is given as 1.250 plus 0 and minus 0.0005. This means that the shaft cannot be smaller than 1.2495. This shaft can be measured with a snap gauge, which is a fixed gauge set to the tolerance specified in the drawing. There are many types of fixed precision gauges. They include snap gauges for outside dimensions, ring gauges, also used for gauging outside dimensions, plug gauges, used for internal dimensions, taper plug gauges for internal tapers, taper ring gauges for external tapers. In some plants, there may be hundreds of sizes and kinds of fixed gauges, each designed for some particular part or group of parts. Snap gauges are fixed gauges designed for taking outside measurements. They are made in a wide variety of sizes and designs. One of the most commonly used types is represented here. It has a large flat gauging surface called the anvil fixed on one jaw and two gauging buttons in the other jaw. One, which is called the go button, is set at the maximum dimension allowed by the tolerance which is specified for the work. And the other, which is called the not go button, is set for the minimum dimension allowed. The difference between the two is the tolerance allowed by the gauge. Fixed gauges should be used with care to reduce wear and to maintain accuracy. The correct way to gauge a round piece is to place the anvil gently on the work and with a smooth rolling motion push the go button past the work. If the go button passes the work and the not go button is stopped, the work passes inspection. If the go button does not pass freely, the gauge should not be forced. Remember that the go button is set out as far as the tolerance will allow. Forcing it past an oversized part may damage the gauge and render it useless for precision measurements. Handling the gauge in the correct manner will assure its precision over a long period of time. To gauge a small part, it is rolled gently into the gauge and under the go button. If it is stopped by the not go button, its dimension is within the tolerance allowed. The gauge is marked to indicate the size to which it is set. This one shows that work smaller than 0.502 and larger than 0.498 will pass inspection. Snap gauges are also used to gauge distances between parallel surfaces. In gauging parallel sides, the gauge should approach the work so that the gauging members are square with the surfaces to be gauged. Only a light hand pressure should be used. If the work is between the limits set up in the gauge, the not go button will not pass the work. However, if the work is undersized, the not go button will slide by. This usually indicates that the work must be scrapped. Adjustable limit gauges, such as snap gauges, can be set to a precise dimension only through the use of master gauges or precision gauge blocks. Such adjustments are made in the gauge control department of the manufacturing plant and should never be attempted without suitable facilities and experienced skill. Go, not-go ring gauges are used for checking outside dimensions of round parts. In use, the gauge should approach the work straight and be brought over it without twisting or turning. The not-go ring gauge can readily be identified by its annular groove. Taper ring gauges are used for checking both the size and the angle of tapers. If the work cannot be shaken in the gauge, the angle of taper is correct. When the small end of the work lines up with the limit mark, it is of the right size. Screws are gauged with thread ring gauges and other special types. The work should pass freely into the go gauge. Be sure there are no burrs on the work. They will prevent the thread from entering the gauge. The thread should not enter the not-go gauge for more than 1 1/2 turns. A convenient tool widely used for gauging screw threads is the roll thread snap gauge. It is capable of much more rapid use than most other types. The work should pass the go rolls freely and, of course, should be stopped by the not-go rolls. Gauges used to check dimensions of holes are called plug gauges. Plug gauges are divided into two principal classes: straight plug gauges and taper plug gauges. Single plug gauges are made for a single fixed dimension and are not used where work has to be gauged between tolerance limits. The size is marked on the end. Go, not-go plug gauges are capable of gauging a hole within the limits set up in the gauge. Go, not-go plug gauges, such as this one, have gauging members at both ends and are called double-ended gauges. The size of each gauging member is clearly marked. The go end enters the hole freely. The not go end, which is the shorter of the two, should not enter. Another type has the go, not go gauging members arranged in steps. This type is called a progressive plug gauge. On a blueprint, we see the dimensions of a hole as 0.624, plus 0.001 and minus 0. To gauge this hole in the finished work requires a go, not go plug gauge, which will have one gauging member with a diameter of 0.624 and one gauging member of 0.625, a difference between them of 0.001, the tolerance allowed. If the hole has been properly made, the go gauging member, 0.624, slips readily into the hole, but the not go member, 0.625, will not enter, indicating that the hole passes inspection within the tolerance allowed on the drawing. The accuracy of any fixed gauge is classified according to the type of work for which it is designed. Some gauges are made to within a few 100,000ths of an inch of the rated gauge size. To maintain such a degree of accuracy in the gauge demands the greatest of care in its use. The edges of a hole should be smooth. Any burrs, if they are present, cause undue wear. The hole should be clean and free of foreign particles. If not, the lapped surfaces of the gauge may become scratched and worn. A plug gauge should go straight into the hole and should not in ordinary use be rotated as it goes in and out. If the straight in and out procedure is followed, less wear will result and the accuracy of the gauge will be maintained longer. Even with the greatest of care, gauges wear and must be checked periodically on precision instruments. If worn beyond the limits allowed in the shop, they must be replaced. Taper plug gauges are made in many sizes and with various angles of taper. They are used to gauge both the sizes and the angles of tapered holes. This is a number 2 Morse taper plug gauge. The limit mark is in the form of a fine groove encircling the gauge. This gauge checks both the angle of the taper and the size of the hole. If the taper is correct, the gauge cannot be shifted sideways, and if the hole is of the right diameter, the limit mark will line up with the end of the work. Another type of taper plug gauge has a tang at the small end. It is used to check the tang recess, if such exists in the part, as well as the taper and hole diameter. If the tang readily enters the recess and the taper fits the hole snugly, the part passes inspection. Taper plug gauges are made in a great variety of sizes and angles of taper. The limit mark on this one is in the form of a flat. A widely used type for checking internal dimensions is the flat plug gauge. Go and not go gauging members are on opposite ends. This type is particularly useful in gauging large holes. Its light weight contributes to ease in handling. Another kind of gauge, usually of special design for each specific job, is the flush pin gauge, widely used for checking depth dimensions. The pins are brought into contact with the location to be gauged. The tops of the pins are cut in steps to the limits allowed. The lower step should be flush with or be below the top surface of the gauge. The higher step should be flush with or be above it. Screw plug gauges used for checking internal screw threads are made in a large variety of sizes and shapes. Screw plug gauges usually have a chip groove cut for the full length of the thread on the go end of the gauge for the purpose of clearing chips out of the thread to be gauged. The gauge should enter the hole freely and should be run down to the bottom. The not-go end should not enter the hole more than 1 1/2 turns. Mass production depends upon fixed gauges for quick and accurate gauging of interchangeable parts. Constant inspection of products must be maintained to assure the precision required for interchangeability, and for this reason, fixed gauges are the special tools of the inspector. The gauges employed for inspection must be used with the same care as those used for gauging work while it is being produced. But careful use is not enough. All gauges must be checked periodically with master gauges or gauge blocks to determine their precision. For this reason, one of the most important sections of a modern plant is the gauge control or gauge inspection department, where all gauges and other measuring tools are checked and adjusted. Here we see precision gauge blocks being used with an electrolimit gauge to check the accuracy of a flat plug gauge. Precision measurement and its control depend upon the operator's skill and care in the use of his gauges. All these elements together make possible the successful interchangeability of parts required in mass production.